Hello students, I am Mohana and this video is going to be all about chemical hybridization. I have seen many students struggle to understand the concept of hybridization. So in this video, I am going to address two key points. What is hybridization and why do we exactly require the concept of hybridization? So let's get started.
What is hybridization and why do we require to study the concept of hybridization? These are two very basic questions which crop up in our mind when we encounter this chapter, when we encounter the chapter of chemical bonding. So before going deeply into this concept, I would like to recapitulate some very important concepts of valence bond theory or VBT. So valence bond theory is an extremely important theory which introduced to us the concept of atomic orbitals. So atomic orbitals are orbitals which are present in two atoms which are undergoing covalent bond. So valence bond theory enabled us to visualize the formation of a covalent bond with the help of atomic orbitals. So when the orbitals or atomic orbitals of two atoms overlap, a covalent bond forms. So this is a very interesting concept. And now let us go to the third point, which tells us about the formation of the sigma and pi bonds. So sigma bonds form when orbitals overlap head to head, while pi bonds form when orbitals overlap side to side. So these are the key points which VBT or valence bond theory told us. But now we'll be studying hybridization in this video. The basic bookish definition of the hybridization is atomic orbitals can combine to form new orbitals called the hybrid orbitals, which have different energy levels and shapes. So I know this is very difficult to understand just by looking at the definition, but we will be discussing with the help of a very simple example. So let's get started. Let us start from a very simple molecule like CH4. This is popularly known as methane. Okay, so let us assume that a concept called hybridization doesn't exist at all. So at that point of time, how will we carry out covalent bonding between one carbon atom and 4 hydrogen atoms? How to do that without hybridization? Since you guys don't know about hybridization at all, so let's start with the basic electronic configuration of carbon atom. The electronic configuration of carbon atom is 1s2, 2s2, 2p2 because the atomic number of carbon is 6. Okay. The electronic configuration of hydrogen is 1s1 because the atomic number of hydrogen is 1. Okay. So now before moving on to the next part, it is very important to know that the filling up of electrons are taking place with the help of Aufbau principle. It follows the Aufbau principle. Okay. So now carbon in the ground state kind of looks like this. The 1s atomic orbital is a box, looks like a box. The 2s atomic orbital also looks like a box, and this is the 2p atomic orbital. Let me fill up the electrons over here. 1s, 2s is also fully filled and 2p has 2 electrons. Let me label them as well, 1s, 2s and 2p. Now hydrogen, as we know, only has 1s orbital which has only 1 electron residing in it. Now there are 4 hydrogen atoms. While bonding of carbon with hydrogen is taking place, there is something called a bond energy or bond enthalpy which is released to stabilize the carbon hydrogen bond. So the release of bond enthalpy or bond energy leads to the stabilization, leads to the formation of a stable CH bond. Okay, so this bond enthalpy has a very huge role in bond formation. How? Let us see that. Okay, so here carbon was initially in its ground state, but there is a bond energy. The bond energy which was released with the addition of carbon and hydrogen with the interaction, not addition, with the interaction of carbon and hydrogen, a bond energy was released, and that bond energy was utilized in exciting the ground state of carbon into its excited state. So this bond energy basically helped the ground state, the carbon in its ground state to reach its excited state, and this bond energy was released due to the interaction between the carbon and the hydrogen atomic orbitals. So carbon ground state looked like this. So what will happen? What things will happen which will lead to carbon reaching its excited state? So what is exactly carbon's excited state? What happens over here is actually one electron from 2s orbital jumps. It basically jumps to the vacant 2p orbital, and the energy required to for this process to happen is known as the promotional energy. The energy required for this process to happen is known as the promotional energy. So now let us have a look at the carbon excited state. So it somewhat looks like this. I am only drawing the valence orbitals. Why? Because 1s does not participate in bonding. Why is it so? Because 1s is not a valence orbital. Only those orbitals which participate in bonding only should be written. Okay. So this is 2s and this is 2p, and since one electron jumped from 2s to 2p, 2s will only have one electron and 2p will have one. This will also have one, and this atomic orbital, obviously it was vacant over here in the ground state, but in the excited state it is singly occupied. Now we can clearly see that 2s is also half filled and 2p is also half filled, and this is extremely stable. Now there are 4 hydrogen atoms. We already know that CH4 has 4 hydrogen atoms, and these hydrogen atoms, each of them will form 1-1 bond with these half-filled atomic orbitals. Now what happens is that there are some conclusions which we arrive at. After doing all these things, we arrive at some conclusions. The first conclusion is that you can clearly see one hydrogen atom is bonding with the s orbital of one carbon atom. Or I should not write the s in. Okay, I should write the s like this. So this hydrogen atom is bonding with the s orbital of carbon atom, and there are other 3 hydrogen atoms which are bonding with the px orbital of carbon atom, another one is bonding with the py orbital of carbon atom, and another one is bonding with the pz orbital of carbon atom. So we can clearly see that 3 hydrogen atoms are bonding with the px, py and pz, while one hydrogen atom is different from the others and is bonding with the s orbital. So as a result, the bond energy and bond length of this CH bond is different, and it is probably smaller, because bonds which have a higher S character, they are smaller, that we will discuss later on. But this bond is presumably smaller, and these 3 bonds are longer. So the bond energy is different, and these bond lengths are smaller, are longer. Okay, so this is the first conclusion. The second conclusion is, we already know from atomic structure chapter that px orbital is perpendicular to py atomic orbital, which is again perpendicular to the pz atomic orbital. So what happens over here? Since carbon is bonding with one hydrogen atom with its px orbital and another hydrogen atom with its py orbital, so the HCH bond angle should be 90 degrees. Don't you think that? Because px is perpendicular to py, so if this is px and this is py, the angle between them, the angle between the HCH bonds will be 90 degrees. Okay, so here the angle is 90 degrees. And the third thing over here is, if the HCH bond angle is 90 degrees and the bond lengths are like the way it is shown in the first conclusion, then the geometry of this CH4 cannot be tetrahedral. Okay, why am I saying this? I will be explaining it. Okay, now these are the conclusions, these are the theoretical conclusions which we have arrived at without the involvement of the concept of hybridization. But now if I show you the experimental observations, the first experimental observation for CH4 molecule is that all bond lengths in CH4 are identical. All bond lengths are identical, and this is directly contradicting our first conclusion where this bond length was different and these three were different. They were different to each other. Okay, so this directly contradicts the first point. The second point is all bond angles are equal and they are equal to 109 degrees 28 minutes. So here also this contradicts the second point where the HCH bond angle was coming to be 90 degrees. So this is directly contradicting the second point. And third point is that the geometry of CH4 is tetrahedral. So this is very interesting because we can see clearly that all the three conclusions which we arrived at theoretically, they are totally different from the experimental observations. So we must be missing something, and that is when the scientists thought about the concept of hybridization. The concept of hybridization was brought about by the scientists to match their experimental observations with their theoretical calculations. So let's get started. Let's try to understand what is exactly the theory of hybridization. So here, let us start with the carbon excited state, carbon ground state and everything, the excitation with the help of bond energy, the promotional energy, everything is same, nothing changes. But now the main fun comes in. Okay, so we'll just draw the 2s and 2p because only 2s and 2p are participating in bonding because they are the valence orbitals. So this is the carbon excited state. Now what happens? There are 4 hydrogen atoms, and since there are 4 hydrogen atoms, and energetically we know 2s has a lower energy than 2p. So now just think about it. There are 4 hydrogen atoms. So each of them will want to be stable. Each of them will want to have a more stable bond. So they will all fight with each other. They will have a very huge fight because everybody will want to bond with 2s orbital, because 2s orbital is energetically 2s orbital has a lower energy than 2p. Everybody wants a lower energy, everybody loves stability, and all the hydrogen atoms will fight heavily to bond with 2s, and as a result carbon atom will become unstable, carbon will become mad. So what happens? Carbon is very intelligent. So what carbon does, the carbon just rearranges itself a bit. So carbon rearranges itself and it forms carbon hybridized carbon. So what it does, the carbon mixes 4 of its orbitals, mixing of atomic orbitals, and after mixing its atomic orbitals, it forms hybrid orbitals. And these hybrid orbitals all have same energy, and their energy is lower than that of the original atomic orbitals. Okay, I hope you can read whatever I am saying because I am also speaking all those things which I am writing. Okay, so the mixing of this atomic orbitals s and 1s and 3p orbitals, it takes place to form hybrid orbitals, and the hybrid orbitals are 4 in number because we have 1 s orbital and 2 and 3 2p orbitals. Okay, so we have 4 hybrid orbitals. So, and the 4 hybrid orbitals thus formed have same energy, all have the same energy, and they are their energy is lower than that of the original atomic orbitals. So usually the energy of the hybrid orbitals are lower than the original atomic orbitals. Okay, now what happens is that let me again write down the carbon hybridized orbitals. There are 4 of them, and the electrons still reside singly in the hybrid orbitals. Now, what is the name of hybrid orbital? Because one s is coming together with the 3p orbitals. So s and p, one s is coming together with 3p. So when we combine an s and p orbital, we get sp3, because that is 1s and 3p. So each hybrid orbital, they are now no longer purely s and no longer purely p. They become sp3. Each of them become sp3. So as a result of that, what happens is that now when we have hydrogen, we have 4 hydrogen atoms. All the hydrogens are very satisfied because they see that they don't have to fight with each other at all. Each and every hybrid orbital have the same energy. They have identical energy. And so the hydrogens are very relaxed. Each of them can now very well bond with each of the hybridized orbitals, and nobody has to fight with the other person. So now the conclusion which we reach after the bonding of the hydrogen with the hybrid orbitals is that the first is the CH4, all bond angles are seen to be 109 degrees 28 minutes. And since all bond lengths are equal, since all hybrid orbitals are have the same energy, so since all the hybrid orbitals have this identical energy, they have the same bond length or identical bond length. So you can clearly see that the the experimental conclusions, the experimental observations which we had arrived at, they are all coming true. Now the bond angle part, yeah, this one is also coming true, and it is corresponding with our experimental observation. Now the third thing over here is any sp3 hybridized orbital, any molecule which have sp3 hybridized orbitals, they have a geometry which is tetrahedral. It has been checked with multiple sp3 hybridized orbitals, multiple molecules having sp3 hybridized orbitals. Okay, so they have and sp3 hybridized orbitals have a definite shape and structure. This is what we conclude. Okay, so this is how beautifully we concluded, we matched all our experimental data with our theoretical data by just introducing the concept of hybridization. So hybridization is nothing but mixing of the atomic orbitals to create a new form of orbital, which is the hybrid orbital. Why is it hybrid? Because it is neither purely p nor purely s. It is a mixture of s and p, and that is why it is hybrid. They all have the same energy, and their energy is lower than that of the original atomic orbitals. So I hope everything is clear to you, and I'll be talking about other types of hybrid orbitals like sp and sp2, sp3d, and there are many other hybrid orbitals which we'll be discussing in the future videos. Thank you and God bless you.